Welcome to Online Precalculus. Today, we're going to talk about section 4.7, which is inverse trigonometric functions. So in this section, we're going to take the last few sections where we graphed the sine, cosine, tangent, cotangent, secant, and cosecant. And we're now going to see what the graphs of the inverse sine function look like, which we use a little bit to solve problems in right triangles. So now we're going to look at the graph and see what it looks like. So we're going to understand and use the inverse sine and the inverse cosine and the inverse tangent. And then we're going to use our calculator to evaluate some inverse trigonometric functions. And then we're going to find exact values of composite functions with inverse trigonometric functions. Okay. So what is the most important thing you should already know about inverses? Okay, from way back in chapter 1 when we studied inverse functions. So some things you should know is that if there is no horizontal line that intersects the graph of a function more than once, it's called a one-to-one function and has an inverse that is actually a function. If it doesn't have that, then the inverse, it might have an inverse, but the inverse is not a function. If we have a point A, B on the graph, then if we switch the x and y, point BA is on the inverse function denoted as that symbol, which means F inverse. And the graph of F inverse is a reflection about the line y is equal to x. So all this is stuff that we've covered in the past and that you should know about inverse functions. Okay, so let's then start with the inverse sine function. Here's a graph of the sine function. Okay, you can see that it clearly does not pass the horizontal line test. That means if we were to flip this thing around across the line y is equal to x, it would not be a function. Just like a parabola. But a parabola is kind of similar to a square root function with its inverse. So that means if we took half a parabola, then we would get a square root function. And these two functions are inverses of each other. So basically with a parabola, what we were able to do is we were able to limit the domain in order to make a function that has an inverse function. Okay, we're going to do the same thing here with the sine function. Okay, we are going to limit the domain, and you can see it better here, from here to here. We're going to start at the bottom and we're going to go to the top, and this is now the limited sine function. Okay, it starts at negative pi over 2. It goes to a positive pi over 2. Okay, so with this restricted domain, every horizontal line that can be drawn between -1 and +1 intercepts the graph only once, and therefore this now passes the horizontal line test and is one-to-one. So on the restricted domain of negative pi over 2 to positive pi over 2, the sine has an inverse function. Okay, and the way we write this, we've seen this before, is inverse sine of x or arc sine of x. They mean exactly the same thing. Personally, I prefer this one because it is less to write. And the -1 exponent kind of looks cool, even though it's not an exponent. It's just notation. Okay, and it has the same symbol as the inverse function notation. Okay, so I tend to use this one over arc sine. Is that and that the same thing? No. The inverse sine is an inverse sine function. If we put the exponent out there, it means the reciprocal of sine, which is the cosecant. Those two are not even close to the same. Okay. The inverse sine is a special function, right? It's the inverse of the sine function, and we'll talk about a little bit more what that means in a second. Okay. So one way to graph the inverse sine is to take the points on the graph of the restricted sine function, like these three key points, negative pi over 2, -1, 0, 0, and pi over 2, 1, and flip them around to give me -1, -pi/2, 0, 0, and 1 pi/2. And then we would use those 3 points to sketch the graph. Here is the sine function. Here is my inverse function. This function has an x value of -pi/2 and +pi/2. This function has an x value of -1 and +1, and y values of -pi/2 and +pi/2. Everything just gets reversed. We switch x and y. And you can see that on the third graph right here. You can see that the two are reflections of each other across the line y is equal to x. Makes sense. Pi/2 is about 1.57. So, you know, a little bit above 1 in both of these graphs. Okay. So, if we were to then, we'll come back to this a little bit, but if this is considered the parent function right here, all of my transformations still hold, which means I could move this function up, down, left, right, stretch it, compress it, reflect it. So that means if you would see something like this, knowing what the inverse sine function looks like, this would clearly have the effect of shifting the graph 1 to the left. So I know that the inverse sine has a coordinate of 0, 0. So if I want to shift that left, it should be -1, 0. And my answer would be D. And we'll get into a few more transformations a little bit later on. But let's talk a little bit about what this means. So if you want to find the exact value of the inverse sine, it can be found by thinking of the inverse sine as the angle somewhere in between -2 and -pi/2 and +pi/2, whose sine is something, whose sine is x, right? Inverse sines give you angles. All right, the sine function gave you the y coordinate at a specific angle, like the sine of theta equals a number. Well, in this case, the inverse sine of a number equals an angle. So the input is going to be an angle, and the output, or sorry, the input is going to be a number, and the output is going to be some angle in my interval. Okay, so something like this. The inverse sine of -1. It's asking you an angle whose sine is -1, and that is -pi/2. And then the inverse sine of 1 is +pi/2. So we're thinking of inverse sine in terms of an angle, and we're going to represent this angle by usually theta. Okay. So if you want to find the exact values of the inverse sine, you can do this by realizing that the relationship that the inverse sine, the output of an inverse sine, is an angle. And you can just rewrite this as the sine of an angle is equal to whatever is inside the sine. But we needed to restrict the domain. That comes in very important later, that the angle must be between -pi/2 and +pi/2. And the exact value table is stuff that comes right from the unit circle, stuff you should know. Okay, so here's the fourth quadrant if we're going in a negative direction, and here's the first quadrant if we're going in a positive direction from 0, 0. My thetas, my sines. Okay, so if I want to find the exact value of radical 2 over 2, this was on the table on the last page. It's on the unit circle. Okay, the way I can write this is that some angle is equal to the inverse sine of the square root of 2 over 2, which means that the sine of some angle is equal to radical 2 over 2. And my question is, what is that angle? And so theta is pi over 4. Double check, and we can see pi over 4 is radical 2 over 2. the outputs of inverses are angles. So I'm usually going to have an angle in terms of pi as my answer. For the sine of radical 3 over 2, okay, you can go through the whole process of writing this out. We'll do that for now. That's theta is equal to the inverse sine of radical 3 over 2, which means that the sine of some angle is radical 3 over 2, and that angle is equal to pi over 3. Again, right from the unit circle, check your unit circle and make sure you're getting these angles right. Now, as we get a little bit later, not all of these angles, not all of these numbers will be something so recognizable from the unit circle, but for now, let's stick with the easier ones. Okay, so let's move this down a little bit. So find the exact value of the sine of negative 1/2. Okay, so I got to ask myself, where on the unit circle is negative 1/2? And hopefully you're thinking that it's at 11 pi over 6, but that is not in the domain of the inverse sine. It has to be one of these angles in between negative pi over 2 and positive pi over 2. So instead of going all the way around the circle, instead of going all the way around the circle like this to get to my negative 1/2 as a y coordinate, I'm just going to go this way. So the answer to this is that theta is some angle that has an inverse sine of negative 1/2. The sine of some angle is negative 1/2, and that angle is negative pi over 6. Same thing for this one, is that theta is equal to the inverse sine of negative radical 2 over 2. The sine of something is equal to negative radical 2 over 2. And so theta is that angle whose sine is negative radical 2 over 2, and it is negative pi over 4. Not 7 pi over 4, right? Negative pi over 4. Theta has to be between negative pi over 2 and positive pi over 2. Okay? Some inverse sines cannot be evaluated because the domain of the inverse sine function is between negative 1 and positive 1. It's only possible to evaluate inverse sines for values of x inside of this domain. So the inverse sine of 3 is not possible. There is no angle between negative pi over 2 and positive pi over 2 that gives you a sine of 3. It only goes from negative 1 to positive 1. Okay, so just be careful with that. Same thing with cosine. Again, fails the horizontal line test if we leave it by itself. If we went from negative pi over 2 to positive pi over 2, it would fail the horizontal line test as well. So we need a different domain for cosine, and we start at the top, finish at the bottom. So the domain for the inverse cosine is going to be from 0 to pi. And basically it's one quadrant where the, let's go back to the graph. All the way back, it's a little far, but, oh geez. Okay, so one quadrant where the sign is negative, one quadrant where the sign is positive, right? The closest one to 0, right? That's the best kind of way we can get at that. So for cosine, it's the same thing, right? We're going to take one quadrant where the sign is positive or cosine, and one quadrant where the cosine is negative. So that way we get all the values between 1 and negative 1. Okay. So the inverse cosine, same notation, is the inverse of the restricted cosine function. And if we have y is equal to the inverse cosine of x, it means that the cosine of y is equal to x. Same as last time, except the angle must be between 0 and pi, and my x values must be in between negative 1 and positive 1. So in order to graph this, again, same thing. We're going to take the restricted cosine function here and just switch these x's and y's. So this one becomes 1, 0. This one becomes negative 1 pi. So you get this little swoop that goes a little bit backwards. Okay. Domain here was 0 to pi, range -1 to 1. Domain and range switch because they are inverses and we're switching x and y. As far as my table of values, again, we're going to think about the inverse cosine as the angle on the interval between 0 and pi whose cosine is x. Table of values come right from the unit circle, and they're mostly the same types of numbers. So if you see an inverse sine or cosine with a 1, with a radical 3 over 2, with a radical 2 over 2, a 1/2 or a 0, or any of the negatives, you know you can evaluate that without using a calculator. Right? There are some that are not going to be like that, where we're going to use a calculator next, after this. All right, so find the exact value of the inverse cosine of negative radical 3 over 2. So it's not a negative angle, because negative angles in the fourth quadrant, the cosine is positive, right? The x-coordinate is still positive in the fourth quadrant. So we're looking for an angle whose inverse cosine is negative radical 3 over 2. So that means there's an angle where the cosine of theta is equal to negative radical 3 over 2, and that angle is 5 pi over 6. Okay. And I like to use the reference angle so I can think about what angle in the first quadrant and then move it to the second quadrant. But, you know, however it is that you think about how to get these answers is fine. All right, let's just jump right to the answer here. The cosine of negative 1/2 is the angle whose cosine is negative 1/2, and that is 2 pi over 3 for theta. Okay. Got to do one more, right? Tangents. So tangents, here is my tangent line, right? We can see that it repeats itself. So in order to pass the horizontal line test, I just take the one cycle in blue, right? The negative and the positive, except this is one whole cycle as opposed to sine and cosine, which was only half a cycle, but it doesn't really matter. Okay. If I look at my domain and range of the of the tangent function, right? The domain was from negative pi over 2 to positive pi over 2, not including those two. And the range is from negative infinity to positive infinity. So when you flip those over, the domain is now unlimited, so I can plug in anything I want, but my range is only going to go from negative pi over 2 to positive pi over 2, but not including them like I did in the sine and cosine. Okay. So again, same notation, inverse tangent is the inverse of the restricted tangent function from negative pi over 2 to positive pi over 2. Same definition, that if y is equal to the inverse tangent of x, it means that the tangent of y is equal to x. But I can just, basically I'm just taking the tangent of both sides, and the tangent and the inverse tangent undo each other, usually. Okay. So here's my table of values. My steps are going to be the same. Start with my question, rewrite it like that if you want to, or just remember my table of values that I can get my tangent values from the unit circle. Okay? And again, these should be kind of familiar. And if you have a number that's not one of these, there's other techniques. All right, so let's start with this. So theta is equal to the inverse tangent of the square root of 3. So that means that the tangent of something is the square root of 3, and that something is pi over 3, right from my unit circle. All right, remember what tangent means? It means the y-coordinate divided by the x-coordinate, so you could always divide the two coordinates to figure it out. Here, theta is equal to the inverse tangent of -1, so theta is the place where the tangent is -1, and that is negative pi over 4. All right, so are the domains of the restricted trigonometric functions the same as the intervals in which the non-restricted functions complete one cycle? Yes for tangent, no for sine and cosine. Okay, so remember the period of sine and cosine was 2 pi. The period of tangent is pi. So we're only looking for one positive quadrant and one negative quadrant. So the domain of the restricted functions for sine and cosine are including negative pi over 2 to positive pi over 2, 0 to pi, including, but not including the endpoints because they're asymptotes for tangent. So these are the only two that match the domain. All right, all the others are going to be a little bit shifted. Okay, so the domain of the inverse function is going to be a little bit different than one period of the original function. And here's what they all look like put together. So this summarizes the graphs of the three basic inverse trig functions. And again, if we wanted to, we could shift these up, down, left, right, stretch, compress, reflect, but we're not going to go too crazy with that with graphing like we did in previous sections. Okay, we just want to get sort of like the hang of how to use these functions, and less so with having to go crazy trying to graph them. The easiest way to graph these things with a bunch of shifts on it would be to graph the original function and then just switch the x and y coordinates, right? And then just draw it that way. Now, for most problems, you can pretty much use a calculator to evaluate inverse functions. Okay? For every calculator that has sine, cosine, and tangent, somewhere there is going to be an inverse sine, an inverse cosine, and an inverse tangent. Usually they're not buttons. Usually you have to press a shift or a secondary function to get to, usually they're written above the sine, cosine, and tangent. Every calculator is a little bit different, so just be sure to look at your calculator and see how you would go to access those keys. So we can use a calculator for some of these. So the key is, when you do these, just make sure you know what mode your calculator is in. Okay, so this is a output. So when I get my answer, it's going to be a angle. And in my case right now, I want it to be in radians. Okay, so if I take 1/4 and I take the inverse sine of that, I should get 0.2526. All right. If your calculator was in degrees, oh, let's hold on, put it back to degrees. Degrees, inverse sine of 1/4 would give me 14.47 degrees. Okay. So you got to be careful and determine what the question is actually asking you. For most word problems, we're probably going to wind up using degrees. For triangles, we're probably going to use degrees. But for some of these other type of questions, they might want the answer in radians like they do right here. Here, again, this is okay. It's okay to have a tangent that is -9. The domain for inverse tangents is from -infinity to +infinity. I can plug in anything I want. So let me switch my calculator back to radians, and the inverse tangent of -9.65 should give you -1.4675. Okay? Make sure you're getting these on your calculator. Again, if you try to plug in this, the inverse cosine of 3, your calculator is going to spit out error, syntax error, undefined, whatever it is, however it winds up doing that. Okay, so now let's do some function compositions. So this should be familiar. When we talked about inverses, you should remember that f inverse of x is equal to x, and f inverse of f of x is also equal to x. This is the definition of inverses. If these two are true, then f and f inverse are inverses of each other, and this is how you prove two functions are inverses of each other. This is a handy feature because it means that if we are on this interval, the sine and the inverse sine just undo each other. And if we're in this interval, the inverse sine and the sine undo each other there, right? So as long as we're in the interval of the inverse sine and cosine, between -1 and 1 here, because we're doing the inverse first, and then the sine can be anything you want. Here, right, this has to be in between -π/2 and +π/2, because that's what the angle is the one that's going to limit us there. The x coordinate is the one that's going to be limiting us there. Okay. And same thing for these two. So you get the hang of these when we see the question. But as long as the thing that we're plugging in is defined, we can just undo each other and get x like this. So the sine of π/4 is radical 2/2. The inverse sine of radical 2, so let's work this out. So the sine of π/4 is the square root of 2/2. That's this answer. The inverse sine of radical 2/2 is the angle whose sine is radical 2/2. So that is π/4. Okay, so that's what this is saying right here. Or sorry, that's what the point of this was. But is it always going to be this? Can I always just say, oh, the answer is just π/4, or the answer is just whatever's here? And that's no. Because what happens here? The answer to this is not 5π/4, because 5π/4 is not in the interval of negative radical 2/2. But you can still evaluate this. It's just not this answer. So the sine of 5π/4 is, well, you can use the reference angle and whatever. So the sine of 5π/4 is negative radical 2/2. Okay. The inverse sine of negative radical 2/2 is negative π/4. So if this term, if this angle that you are not trying, or that you are trying to find the composition function is not in between negative radical or negative π/2 and positive π/2, you're gonna get a different answer. Okay, so that was what this slide right here was saying, that it's always gonna be x if your angle is in between these two numbers. If not, you're gonna have to work it out and you're gonna get something else. All right, so we're doing the inverse first. So as long as this is in between -1 and +1, I'm okay. If it's not, this would be undefined. So the answer here is just 0.6. Okay? Because, and I would have to use a calculator for this, right? So I would calculate this angle, plug it back into the cosine, and I would just undo each other, right? Because a function of its inverse, as long as it fits into the inner function, is good. This, however, is gonna be a problem. Okay, so let's work this out. The sine of 3π/2. That's on the unit circle. Okay, so that is down there, 3π/2. So the y coordinate down there is -1. So now we're looking for the inverse sine of -1. The inverse sine of -1 is going to be the angle whose sine is -1, which is going to be -π/2. So these two do not match. But the answer to this is -π/2. This is undefined. It's too big. Try it on a calculator. It's going to spit out an answer that says it's undefined. Let's try some Gotta problems. Ooh, recognize that? 0.7. Recognize that? Too small. That's the one. That's a problem. The sine, the inverse sine, is only defined between -π/2 and +π/2. So you can do this, but the answer is not going to be pi, because inverse sines do not spit out angles that are not between -π/2 and +π/2. So work this out. The sine of pi is, well, think about it here. Pi is right there. The y coordinate there is 0. So the sine of pi is 0, and the inverse sine of 0 is 0. So the answer to part B is 0. Little tricky, yes, but as long as you recognize what's going on with these inputs, and if they fit into the domain of the function you're trying to do and what comes out of those functions, you'll be okay. Okay. Let's try some things. Let's try some problems where we have something that is not on the unit circle. Okay. And while we could use a calculator for this, it's going to have a lot of rounding errors. It's better to be exact. So we can use points on the terminal sides of angles and standard position to find the exact values of expressions involving composition of function for different inverse functions. So if we remember what the tangent is actually doing, we can sketch out a angle or a triangle even and figure this out. So let's try it. The cosine of the inverse tangent of 5 pi over 12. So that means I want an angle whose inverse tangent is 5 over 12. So that means that the tangent of something is 5 over 12. I don't really care what the angle is because I'm just going to take the cosine of that angle in a minute. But if I can remember the relationship that tangent has with a ratio, like SOHCAHTOA, or that the tangent, even better, since we're going to use angles that are not necessarily in a specific triangle, that the tangent of an angle is the y over the x coordinate, and the cosine of an angle is the x over the r, the radius. I just need to find the radius of the angle in this circle, and the radius is going to be the square root of x squared plus y squared. Okay? Pythagorean theorem. Okay? If I were to draw this out as a triangle and use SOHCAHTOA, I could just call this my angle, and the tangent would be the opposite over the adjacent, and I would use the Pythagorean theorem, just like I'm using right here, to find the hypotenuse. So my radius is going to be 5 squared plus 12 squared, which is 169. So the radius is 13. And I should have known that ahead of time since this is a Pythagorean triple, 5, 12, 13. So the cosine of the angle is going to be the x coordinate over the radius. So the answer to this would be x coordinate 5 over 13. No, adjacent. Sorry, 12 over 13. 12 over 13. The x coordinate, left and right. 12 over 13. Okay. So my cosine of the inverse tangent of 5 over 12 is 12 over 13. So I'm basically going to have to use some sort of Pythagorean theorem type of thing to get my other angle. Let's try it again. So we know that theta is equal to the inverse tangent of 3 over 4. That means somewhere there's an angle that has 3 over 4. So if tangent is equal to x over y, that means x is 3, y is 4. I just need the radius. Using the Pythagorean theorem, we can get that r is equal to 3 squared plus 4 squared. It's 9 plus 16, which is 25. So r is equal to 5. And the sine of some angle is equal to y over r. So my answer would be 4 over 5. So I never actually had to figure out what the angle was. All I have to, because I'm finding the angle whose tangent is 3 over 4, and then the sine of that same angle. So I'm dealing with, I never actually have to solve for the angle. I can just use the ratio right here to get my composition value. Okay. Sometimes they're not so nice. Sometimes they're not a nice Pythagorean triple like they were in the last question. Okay, and this is why you don't really want to use the triangle. You don't really want to use SOHCAHTOA too much, because we now have an angle, or we now have a sine of a negative number. So it's really weird just to try to make a triangle with a negative side. It doesn't really make a lot of sense. Okay, so let's walk through this. This is an angle whose sine is negative 1/3. That means the sine of some angle is negative 1 over 3. So sine of theta is equal to the y-coordinate divided by the radius. So that makes the y-coordinate negative 1 and the radius positive 3, because the radius is never negative. Okay, and so now all we need is the x-coordinate. Okay, so 3 is equal to the square root of x squared plus negative 1 squared. And I can solve this, square both sides. So 9 is x squared plus 1. So x squared is equal to 8. And so we don't really need plus or minus, because again, actually, we need to think about this for a second. If the sine is negative and the radius is positive, when we solve this, we just need to figure out what quadrant we're supposed to be in. Okay? Because the inverse sine has to be, right, this number right here, it has to come from either the first quadrant or the fourth quadrant, or else this wouldn't work. It can't be the first quadrant because it's negative, and the sine represents a y-coordinate. So that means we have to be in the fourth quadrant, which means x in the fourth quadrant must be positive. So square root of 8 is the same thing as 2 square root 2. And now I have my three values. I can find the cotangent. The definition of cotangent is the inverse of tangent. So it's y over x. So my answer is 2 radical 2 over negative 1, which is negative 2 radical 2. Okay. So a lot there just to get to my final answer. Let's try one more of those. Again, fourth quadrant. Okay, so we know that theta is equal to the inverse sine of negative 1/2, and you can skip these steps too if you're getting the hang of this, that the sine of some angle is equal to negative 1/2, which means because the sine of theta is equal to y over r, y is equal to negative 1, r is equal to 2. I just need my x, so I get that, let's just jump right here, 2 squared is equal to x squared plus negative 1 squared, and we get that, square root both sides, and I get that x is equal to radical 3, not plus or minus, just plus, because I know we're in the fourth quadrant and x has to be positive. I now want to find the cosine. So the cosine of theta is equal to x over r. So my answer is the square root of 3 over 2. And I did all that without having to, because you should have realized that that's on the unit circle. So I know the angle. Okay, the sine of negative 1/2 is negative pi over 6. And the cosine of negative pi over 6 is, is negative pi over 6. And the cosine of that is a positive radical 3 over 2. Okay, so you didn't even have to go through all that if you realize that this is part of the unit circle. You do have to do it here because 1/3 is not on the unit circle, and therefore we don't know the sine or the cosine off the top of our head. So some composite functions with inverse trig functions can be simplified to an algebraic expression. These ones are going to get a little weird. We're going to use, to simplify these, we represent the inverse with, we will use SOHCAHTOA in this case, and we're going to use a right triangle. Okay, so first quadrant. Okay, so now we know we can use a right triangle. Let's find the cosine of the inverse sine of x. So in order to do this, all right, remember SOHCAHTOA, right? And we're going to draw a triangle, a right triangle. Okay, here's my angle theta, right? Because we're somewhere in the first quadrant, right? So we're not past 90 degrees this way. That is a ratio. It's just over 1. The sine represents the opposite over the hypotenuse. If I want to find the cosine, I need to find the adjacent side. Okay, so that's the adjacent side. In order to solve for this in terms of x, not x and a, just x, I need to use, again, the Pythagorean theorem. And it says that the two sides squared is equal to the hypotenuse squared. And now to isolate a in terms of x, I subtract x squared from both sides, and I get 1 minus x squared, square rooting both sides. I don't need a plus or minus because, again, I'm in the first quadrant, so I can eliminate all negatives. I'm in the first quadrant because x is in between 0 and 1. Okay. And so now the cosine, so the cosine of this angle right there, which is what I want, is going to be the adjacent over the hypotenuse. So it's 1 minus x squared over x. And I don't need to take it any further than that. Sorry, over 1, over the hypotenuse. Sorry, adjacent over hypotenuse. So we just get 1 minus x squared. If you happen to get a weirder function with a radical in the denominator, you can mess around with that a little bit. Okay. And that was section 4.7, inverse trigonometric functions.